Okay, I'm back with this last exercise of reordering minerals. In this case, I've isolated a group of minerals that are the most important for the fractionation of magmas. And the exercise here is to essentially reorganize the minerals according to the Bowen sequence. And this will help you understand how we move through different crystallization phases, and so we go from mafic assemblages into more felsic assemblages. So essentially we progressively increase the amount of silica. So this information is important. So if we think at the crystallization of a magma, usually we have different batches of magma. We have seen that in earlier lectures. We tend to have that the magma rises in a magmatic chamber or in a system of chambers, and the result is usually the change in composition of the magma. And this change will result in different mineralogy. So let's see how we can represent this mineralogy. So we will start from the bottom, which usually is the top part of the Bowen sequence. So if you remember, we have two trends really in the Bowen sequence. So if I grab some paper, perhaps I can attempt a representation of the Bowen sequence. So we start with essentially a V-shaped diagram. So we will have two sides. And we proceed with a temperature decrease. So temperature will tend to go down with crystallization. So this is low temperature and this is high temperature here. So that's my arrows or direction of crystallization, and on this side we will have the felsic minerals, on this side the mafic assemblages. So if you remember, we start with a mineral called olivine, and here we have plagioclase, and so where are these minerals here? Here is the olivine, classic olive green. So we will place it here, and also this is olivine, and we have plagioclase. So this is the plagioclase, the white feldspar. It's my plagioclase here. Then we move down. What changes usually is starting with calcium-rich plagioclase. We end up with sodium-rich plagioclase here, and then we enter the K-feldspar. So that's your K-feldspar down here. And that's sort of complete with the quartz at the base and muscovite. The assemblages that are on the felsic side. So again, I don't have a sodic plagioclase, so we will not be able to recognize minerals that contain calcium or sodium that are of the same family, but certainly we can place quartz at the bottom of the Bowen sequence, so you can see the increase in silica because this is all silica, and also we have a bit of euhedral quartz in here, and at the same time we can add the phyllosilicate. So increasing water, start to form muscovite, and also on this side we will have the biotite. But yeah, for the moment think about the muscovites as being sort of part of this final phase of crystallization. So we'll often find in rocks associations of quartz, muscovite and biotite, which are in the final phase of the crystallization. We also have to remember that while we progress with crystallization, we can recognize K-feldspar. And so at the bottom, really in the top part of a magmatic chamber, for example, the most fractionated part will be enriched in pinkish K-feldspar. So my K-feldspar would sit roughly here with these other minerals. So K-feldspar, quartz will be often found together. We are left with the last two for the Bowen sequence, so we can push this up. And so we will have the pyroxene following this. Remember, we have an inversion here. We tend to increase the calcium. So here we drop calcium, here we increase calcium. So we go into the calcic pyroxene. So we start with, I think, iron pyroxene and then end up with the calcium pyroxenes. So the Edinburghite diopside series, if you review that in the Zussman, so the book I've recommended, you will find this characteristic transition. And so we have these pyroxenes here, and then we step into the amphibole. So amphibole, and then we have at the bottom we have the biotite. So you see this V-shaped plagioclase, K-feldspar, quartz, muscovite, and on this side olivine, pyroxene, amphibole, and biotite. And of course at the center we have the group of the spinel, which completes our classification, really. So we have a group here of fractionation of spinel. Spinel is in there. So that I think sort of helps you with crystallization idea. So remember, you go from phases that are mostly low in silica and progressively increase the amount of silica until you get to quartz, where it's, you know, more than 90% of the rock will be represented by quartz. These phases usually have also more water, so you have minerals like phyllosilicates that can host the water, which is quite important, as well as the amphibole. You see the transition from pyroxene and amphibole. It's important to realize that you are including more water in here as well, and fluorium many times as well. So I think this was informative. Remember, the plagioclase appears, or calcic plagioclase will tend to sort of drop the calcium, gets more sodic, and then enters into this phase that's more potassic. And this concludes this exercise of Bowen sequence with minerals. Hopefully it gives you a perspective of, you know, a distinction between mafic magmas that will be dominated by olivine and pyroxene versus felsic rocks and magmas that will tend to form, you know, granitic compositions that are dominated by K-feldspar, amphibole, biotite, and also quartz. So there is a logic in how you assemblage the minerals, and the rocks, depending on the degree of fractionation, will contain specific mineralogy. That's the idea.